So today's talk is titled Concepts Behind Deep Learning. Today we will be covering some of the basic concepts that lead to the design of deep learning. Now, the plan of presentation shall be like this. Some very fundamental mathematical concepts. Then I shall try to figure out the links or a shift or the transition the uh, from the machine learning domain to the deep learning domain, definition and relevance of deep learning. We will be focusing somewhat on the convolutional neural network, since that is the basis of deep learning. And then we will find out the current state of art of applications of uh, deep learning. Now, while we start the basic mathematical concepts, the first thing that comes to the picture shall be the data. So here, data shall be primarily configured as scalars, vectors, and tensors. Scalar, vector, matrices, and tensors. These four quantities are used in the neuro computing domain, and more specifically in the deep learning domain. Now, if we are considering a singular value, a single numerical quantity, we can consider that to be a vector. So if we consider a variable, and if it is to be stored, then that particular vector, that particular variable, if it carries something that can be called to be a scalar. A scalar has a value. Then the vector, there is one more term that will come into the picture, that is called a vector. Vector in the deep learning terminology will refer to a positive integer n. A vector is an n tuple ordered multi-set of or array of n numbers called scalars. So if we create a data structure, we call it a vector through a process called vectorization. So the number of elements in the vector is called the order length of the vectors. Vectors can represent points in an n-dimensional space. So here is a pattern vector x. So this x, small x, here is formed by a number of samples, small x1, small x2, small x3, small xn. These can be grouped as a row, as a column. So here vectors will roughly represent a sequence of numbers, a sequence of integers, a sequence of samples, a sequence of points in the sample space. Then matrices, when we group a vectors in some dimension, say m cross n, that will form a vector, that will form a matrix. So if we have a 2 cross 3 representation of vectors, then that will form a 2 cross 3 matrix. So matrix will be required. Then tensor is a multi-dimensional array So it can, in a more general mathematical structure than a vector, we can look at a vector as simply a subclass of a tensor. So with tensors, the rows extend the y-axis and the columns along the x-axis. So if we have a number of matrices to be represented, those can be represented as tensors. So the link from the scalar to the tensor can be like this. Scalar can be one singularity. Vector, if there are multiple such singularities, multiple such values, matrix can be a scaling of the vector in row or column form, and tensor can be grouping of matrices. So that way this link is developed. There is one more concept called the hyperplane. This means that these are connected planes. These are connected planes. Connected planes are required for drawing the discrimination boundaries. Then there is one more concept required, that is of the dot product. So all the computation that will take place in the neurocomputing structure shall be dot product based. So the pattern vectors combining with the weights, connectionist weight W, that will be through a dot product. So dot product is the basic mathematical process that will go on in the layers of a neurocomputing structure. Then probability shall be the basis of decision making. Probability, we know, is a phenomenon that is dependent on chance. So number of trials you make, from that, when we find the number of favorable conditions that will be defining probability, we can link probability with a condition. If we link probability with a condition, that is called the conditional probability. So here we find that if we want to find the probability of A given B, we can first find the probability of A intersection B by probability of B. So that way we can find out the conditional probability. Conditional probability is the basis of decision making. This is based on Bayes conditional probability theorem. Then we need something called samples and population. A population can be the complete group of data. Samples can be a part collected from the population and will be a representative quantity. Not all, but a representative quantity that will have all the features, but in lesser quantity compared to the population. So the sample shall be a subset derived from the population, and it will have all the desirable features, all the relevant features that the population has, and is used for representative purposes. So we can have from the samples collected from the population by doing a random selection. We can do a sample grouping by the use of from a clustered population, and then try to find out some similarity, and then start to do the grouping. So if we have a population with a systematic random sampling, we can create the most relevant set of representation, but in lesser quantity. So the population and sample can have a two-way link, as shown in this diagram, as shown in this particular diagram. So here we find that If we do a sampling from the population, we get a sample, and if we do an inference from the sample, or do some sort of a regression, some sort of a population growth from the sample, we get back the whole of the population. So there is a two-way link between population and sample, and these are very much significant because data in deep learning is quite a critical factor. We might have very small amount of data for doing the training, yet from that small amount of data we can create the complete population of data that can be used for both testing and validation. Now further, when we do a sampling, we have one more group of techniques through which we can do resampling. Since in several situations the sample sets may not be quite sufficient, so in that case we can use resampling techniques. Bootstrapping can be one of the techniques. That means we need to reinforce data. We need to have several versions of the data, several versions of the data created by the use of delay, by the use of minor variations, minor shift in the sequencing, minor shift in the grouping, minor shift in the count. So that way there are several ways through which we can make the quantity of the sampling data go up. Then we can do one more technique called the cross validation, through which also we can have more samples. So there is one more. So as part of the cross validation technique, we can do holdout validation, where data can be grouped as data for training and as data for validation. And if we want to do a validation, we can do a k-fold cross validation. That means we can from the given data set create several sets, k type of sets, where the data are sequenced in k different forms, in k different sequences. So that will give us k different combinations of doing the cross validation. So that can be done by doing a scrambling or de-scrambling of the data. So that means that way the sequence count, volume of data for training, for validation and testing will go up. And if we do all these things, if we make the size of the data go up by doing holdout validation and by doing k cross validation, we call these as part of bootstrapping, bootstrap resampling. So that way we can make the size of the data go up significantly. Now, how to do those k-fold validation bootstrap resampling. So here we can have several cycles. Say supposedly there are k number of cycles. So in the first cycle we can have the first few as test data. Next can be the training data. In the second cycle, we can have from here to there to be the test data. Next can be the training data. Then the third case, we have the test data for a part, shifted part, and the rest for the training part. So that way, by taking different chunks in certain count, we can create different combinations of testing and training data at different training cycles. So that way we will have the data size going up, and the system that way will be a robust one. So how can we do the bootstrapping? So we can do here bootstrapping something like this. So we can do the bootstrapping means to make the size of the data go up. So we can have several sets of training data, several sets of test data. So from the given set of data, we can group in it in the first way, 862958148 like this. Then 3, 7, 10 count for the test part. In the second bootstrap, we can have 10, 1, 3, 5, 1, 7, 4, 2, 1, 8, and then we can have 6 and 9 for the testing part. Then in the bootstrap 3, we can have 6, 5, 4, 1, 2, 4, 2, 6, 9, 2, and we can have 3, 7, 8, 10. That way, many number of sequences can be created. That way, we will have a huge set of data. And that way, the system becomes more robust, and it turns out to be quite reliable one. So we can that way have the training set for tuning the models properly for serving the purpose, and then once the training part is completely done, then only we need to go for the testing part. And for all of those different training sequences, since the test sequences are generated, the test sequences are used once the training sets are fully used. Now, for all these bootstrapping techniques, the network's training and the learning performance is done or is checked by the gradient descent optimization. We have talked regarding the gradient descent optimization in great length. So the basic technique is the least square regression, which will be a difference between the y, that is the target, minus the present weight, scaling the pattern vector, the whole thing squared, and this will be y minus wt transpose with a dot product, doing a dot product with the pattern vector x, the whole thing squared. So this, when we do its or follow its gradient in a downhill manner in such a way that the weight w is continuously tuned and updated till this del e becomes very close to zero. This process will be called gradient descent. This is the basis of the gradient descent optimization. So while we do that, we face local minima and the global minima minima problem. Local minima shall be the lowest point to which the gradient will descend in a local part of the network. Beyond that, in the local part of the network, there will be no further training taking place, and the global minima refers to the minimum value that the complete network gets stuck, beyond which there will be no further decrease of the gradient. In the local minima case, there will be no further training in the local segment of the network, and in the global minima situation, there shall be no further training taking place in the complete network. Why this slide is shown? Because this slide holds key to the formation of the deep learning. Then further, the complete picture of the network comes from the confusion matrix, where we need to calculate the true positive, the false positive, the false negative, through negative and a few other terms like sensitivity, specificity, accuracy, and so on and so forth. Now, these values give the true picture or represent the true nature of the performance of the network once the training, validation, and testing part is complete. Now, since we are now familiar with all these basic notions, and the background is quite set, we can now say that the deep learning its basic concept starts from the traditional ANN. Then we can find that the deep learning has a lot of its characteristics derived from the traditional ANN. Then, though there are similarities of the characteristics, but deep characteristics are somewhat different. If you are that you can have more than three number of hidden layers. Deep learning is characterized by feature learning. You no longer need data labeling. So in the previous case, we found that the ANN required a lot of data labeling. Deep learning no longer requires data labeling. So that is a big change. And further, we can find why we have talked regarding resampling bootstrapping, because huge data sets are required for doing the training. You have more data, your deep learning tool will perform better. Now, just revising our previous neurocomputing background, we can find that the basic neurocomputing lay in the ANN and in the feed-forward configuration, one input, one output, and more than one hidden layers. We can find that these are to be trained with backpropagation method. The multi-layer perceptron is a common example. We can find that each layer may have log sigmoid, 10 sigmoid, or purely linear activation functions, or a combination of these. We can find that neurocomputing structures learns patterns, remembers, and recollects these. These are reliable. These are used all throughout the 1990s and the first decade of 2000, and have been used for a wide range of purposes. The basic versions are the time delay neural network that has the ability to track time variations. They have multiple layers. Then there is one more structure called the recurrent neural network that can have feedback paths from the last end to the middle and to the front end layers. These are used with a time varying input signals, popular with speech processing and time series applications. These are trained with backpropagation in time method. Then there is one more network called the SOM, self-organizing map. That is an unsupervised learning network that is driven by the philosophy called winners take all. So here there will be a competition between the input neurons and neighborhood metrics scaled by the connectionist weights. Now, here are some difficulties. Backpropagation suffers from the local minima problem. Then feature learning was never a satisfactory thing. Required prior learning, data labeling is a factor, and then concurrent and continuous learning rarely taking place simultaneously. And difficulties with the expanding dimensions of data. Therefore, this triggered the shift towards the deep learning. So there are some basic drawbacks. So for these drawbacks, there is a shift towards the deep learning part. Then again, there was a tremendous rise in the number of publications between 2006 and 2016 regarding the deep learning. Why deep learning? From about 2015-16 became a very common theme of research, because there was a tremendous scaling in the number of publications in this 10-year phase, from roughly about 2006 to about 2016. So the graph here clearly shows, and this meant, or this was critical in the growth, or in the shift of preference from the traditional ANN to the deep neural network DNN. Then further, worldwide people found that due to the deep learning facilitated mostly by Google through its app, and through its Gmail, through its mail services, and through the Google search, deep learning turned out to be a very common tool for the common man. Then it facilitated a lot of services in the domains of speech translation, search, robotics, natural language processing, so many things, maps, navigation, routing, and all that. So hence a tremendous rise in the and a tremendous growth of fascination towards deep learning. One more critical factor that is responsible for the tremendous growth of deep learning is the simultaneous growth in the big data scenario. Since deep learning thrives with data, therefore, roughly from about 2016 to the present time, 2020, we find that there is a tremendous rise in the data generated worldwide. So this is a factor further that is driving the growth of deep learning. Deep learning and big data, they both of them go together. They have a symbiotic link. So this link is now critical in the growth of both the scenarios. Deep learning is deriving a major driving force from big data scenario. So this particular slide shows the growth of data. Therefore, we can come to the definition of deep learning. Deep learning, we can say, to be a new branch of machine learning with the objective of making machine learning come closer, through which we can generate near human brain-like decision making. So the deep learning's final goal shall be also a continuation of the goal of the machine learning, is to generate human brain-like decision making capability. So the shift can be shown through this particular slide. So in the classical classical pattern recognition case, since the late 1950s, we found that if we are to do a classification task regarding a car, we need to have a handcrafted uh, feature selector. So through this handcrafted feature selector, we will be selecting some of the key features of the car, and then we will train a simple classifier which we will derive a decision yes or no. But now with deep learning, we do not have a role of the handcrafted feature generator. We have here a trainable feature generator. So there is a feature generator that is built in as part of the deep learning kernel. Further, there will be a trainable classifier. So here, both these two blocks are trainable. There will be a trainable feature generator, a trainable feature extractor, and then there will be a trainable classifier. Both will work together, and then there will be no role of the programmer, of the person. The human role will here suddenly come to an end. So in terms of layers, a very simplistic definition can be, in the previous case, we will have a multi-layer perceptron. There can be one hidden layer, but here, then the deep learning case, we will have more than three. So in terms of network topology, this is a very simplistic difference. So we can have here trainable networks with many layers versus the shallow net. So this can be called the previous generation multi-layer perceptron can be called to be a shallow network, and this one can be called to be a deep network. So we here find that deep networks are characterized as to be groups of trainable networks with many layers, compared to shallow nets where there are just a couple of layers. We can have multiple layers work to build a much better feature set. There will be a characteristic of feature learning, a feature pyramid shall be generated. So the first layer will learn simplistic features. Second layer will learn somewhat more complex features. So the first layer can learn the boundaries. Then the second layer will be learning the combination of the boundaries. The third layers can be learning more complex combinations. So that way, we'll find that a layer by layer learning, and the complexity will start to grow, and the complexity will give more specific or more detailed feature learning. So therefore comes the concept of deep and shallow network. With the shallow network, we have a simplistic feature generator, a handcrafted feature generator. But then the case of a deep learning or a deep network, there shall be no handcrafted feature generator. There will be a trainable feature generator. In the case of the shallow network, there will be a feature labeling, or there will be data labeling. In the case of deep learning, there will be no data labeling. Then in the case of the shallow structure, you have lesser number of layers, lesser number of the middle layers. Then in the case of the deep structures, you have more number of middle layers. So that way you will find that there are more complexity is coming to the deep network, but its performance is more of a is dependent more on a uh, self-sustaining philosophy of working. So there is a difference. Then the case of the cello network, we will have the representations, the middle representations going through few layers of linear transformation. And then in the case of the deep network, we find there will be multiple representations, middle level representations, and they will go through multiple layers of linear transformation. So this is the difference. Now, how can we have deep learning? A few when and why regarding deep learning. Now, why deep? So several people define a deep network in situations where there are more than two middle layers. Then in some cases, people say we can have a deep network when you have unlabeled data. In some situations, people say that when there is no requirement of handcrafted features, you have a deep structure. In some cases, you can have a deep structure when the feature learning is an automatic process as part of the network, as part of the networks learning. So when you have a deep structure, if there are more than one stage of non-linear feature transformation. So when you have more than one stage of non-linear feature transformation, and you have a learning hierarchical representation, you have deep learning generated. So you can have here a car. So from this car, first layer will be capturing the low level feature. Next layer will be generating the mid level feature. Third layer shall be generating the high level feature, and the last layer will be a trainable classifier that will work in tandem with the previous layers. So they will work in tandem. They will work disjointly, but finally they will have a joint or a coupled goal. They will work to reach a common goal. So that particular common goal will have a huge part of feature learning being sustained. The feature learning is part of the network and is one of the fundamental goals. Therefore, deep characteristics or detailed characteristics are captured, detailed features are generated. So we can have here the deep structures are more efficient in representing certain classes of functions, particularly those linked with visual recognition. They can represent more complex functions with less hardware dependence. So you can have here that the deep networks have a trainable feature hierarchy generated. This is the most crucial part. So if you want to do an image recognition, you will find that layer by layer there will be a capturing of the pixel, next the edge, next the detection, next the motif, then the part, and finally the object. While you deal with a text, you will have the feature learning developing layer by layer, starting with the character, word group, clause, sentence, and story. Then speech, starting with the sample, going through the spectral band, sound, phoneme, phoneme, and finally the word. So you will have here a flow of trainable feature transformation taking place layer by layer. So this particular trainable feature transform is key or is crucial in case of deep learning and is responsible for its feature uh, for its capability of deep feature or deep feature learning. So we can find here that this particular process are sustained by learned internal representations, which are sustained by the trainable feature transform. We will find that high level features are more global and are more say 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 uh, uh, are more are invariant to changes and surroundings. So hence are more reliable and in giving better performance. Now let's come to the topologies. There can be three main types. One can be a feed forward type. So there we will find that the feature feeding will be taking place in just a forward manner. So from one leftmost side to the rightmost side, they will go layer by layer. In the second case, we will find that there shall be a feedback type. So from the rightmost side to the leftmost side, the flow will move with the right one driving the next one to the left. Then that layer shall be driving to the layer to the left, and so on and so forth. But in one more case, there is a bidirectional structure where we find that there will be flow two ways, from the left side to the right side, from the right side to the left side. Then we can have several types of training protocol. We can find purely supervised. So all throughout the training, there will be a supervisory uh, supervisory system for governing the learning. Then in one case, there will be unsupervised layer-wise and supervised classifier on the top finally. So most of the layers will be trained in an unsupervised form, and then finally we will have a classifier that will use a supervisory system for doing the classification. Then finally we have an unsupervised learning layer-wise, and then finally we have a global supervised fine-tuning. Then finally we have an unsupervised pre-training. That will be a regularization done through the auto encoders. So these are some of the training procedures that we can use with the deep learning protocols. Now the whole thing started with the back propagation. It gets stuck in the local optima. Convergence is slow, large set and time is required. Then we need to have level data, and in most situations we have unlevel data. Therefore, we need a generative approach for dealing with the situation. So therefore, multi-layer feature learning makes a sense. So a structure of this type is proposed. So here we find that there can be multiple layers through which feature learning will take place. Wait. So here we find that the multiple layer based learning makes a sense. Therefore, a structure of this type is proposed. Now, this particular structure is quite similar to that that the brain has. So brain also has a total of 6 such layers. Those are called the monocular region, then the magnocellular region, then the parvocellular region, and between this particular region there are six layers. So layer by layer the feature learning will take place, and layer by layer these will be shared. So these will be passed on. So this same particular concept is also taken in the deep learning case. So many layer neural network structure should be capable of learning the true underlying features and the feature logic, and therefore shall generalize well. This was the premises by which these particular structures were developed. So then the weight-based learning techniques did not work well with such sort of multi-layer structures till deep learning came, because these particular layers were not good in doing a generalization principles till the feature learning took place layer by layer sufficiently or satisfactorily. Therefore, this particular multi-layer structures with backpropagation driving them throughout, since we're not that much reliable in giving satisfactory results, therefore turned out to be the basis of developing layer by layer feature learning and driving them layer by layer. So therefore, a new way to train multi-layer structures started like this. So the first layers shall be trained first, next that will be driving the second layer. So train this layer first, that will drive the next. Next, that layer will turn the subsequent one. That one is done. Then that will drive the next one. Then it will drive the next one, and finally we'll get the result. And that particular result will be unsupervised sometimes, or will be dependent on some supervisory tuning. So that will depend on the choice. So if we have now the basic concept here shall be to have many layers. So many types of many layers will be there, but the layer by layer learning will take place, and finally one output layer will derive the decision, maybe in the unsupervised form or in the supervised form. So the difference between the structures turned out to be like this. The previous generation ANN structure will look like this, very simplistic, but a deep learning structure will look like this, very complex with many number of layers, and those layers are meant to learn complex features layer by layer. Now, in this case, the basic basic network structure that was responsible for making deep neural networks successful is the convolutional neural network. Now, here we find why the word convolutional comes, because its data feeding process is based on the convolutional process, is based on the convolution. So here there will be some masks. These will be masks, some size mask m cross n. So m cross n will read the weights. Supposedly that is a matrix, a picture. So from this picture, these masks may be 3 by 3, 4 by 4, 5 by 5. They will read layer by layer. They will read row wise, column wise, and then do a convolution, then pass on these to next layer. So here you will have here a convolution layer. So we can see here that from this particular frame, a convolution layer will be generating a few few feature maps. These will be then subsample, means those sample sizes will be subsample, means that shall be shrinked, means its size shall be decreasing. Once those are subsample, you have a few more feature maps. These particular feature maps shall be once more passed on through one more layer of convolution. They will generate one more set of feature maps. Those will be again subsampled. Then we will have a one more layer of feature maps, and those particular feature maps will be finally passed on to a fully connected classifier layer. That particular classifier layer will use a supervised or an unsupervised training, and that will generate the decision finally. So there will be multiple combinations of convolution, subsampling, convolution, subsampling, convolution, subsampling, that will generate feature maps layer by layer, and finally at one point of time a feature set will be fed to a fully connected classifier layer. That particular classifier layer shall be responsible for doing the classification. So here we can see it. So we can see here is that here supposedly there is a numeral. Its size is 3 by 3, and we take a 5 by 5 convolution map here masks. Now these 5 by 5 convolution masks will be generating feature maps of 28 by 28. These are again subsample. These will be generating 14 by 14 feature maps. These are passed through 5 by 5 convolution layers. These will be generating 10 cross 10 feature maps, subsampled, weight 2 by 2. Then we will have 5 by 5 feature maps. These particular feature maps are passed through a fully connected classifier layer that will lead to classification. So this particular process now has a few blocks. First is the input, then is the feature learning layer. So this is the most crucial part. A huge segment of the task is done in this particular layer, feature learning, and finally classification is a smaller part. So we can see here that roughly we can find that the feature learning layer and the classification layer, the main things, you can feed the CNN structure, and once you feed that, you will have a combination of a convolution layer, then a rectified linear unit or ReLU. Then you have a subsampling layer called the pool layer. So this particular combination of convolution, ReLU, and pool, convolution, ReLU, and pool will be repeated multiple times. Sometimes 4 times, sometimes 8 times, sometimes 16 times, 32 times, 64 times. That will depend on the data complexity, data volume, and the nature of the use, nature of the purpose. So finally, when all these feature learning will take place, that will be fed to a fully connected layer that will lead to the classification. So let's see a case here. So we have a bird. We want to do the recognition. Normally, birds recognition is done through its beak. So you need to cut the beak out and then find out if the beak or the beak will be now used for doing a recognition of the bird. So you will bring out the beak, pass through a convolution mask, then add it, then pass it through an activation function. Then the beak detector will be like this. So can represent a small region with few parameters. So some patterns will be seen in different places. They can be compressed. Then something about the training. A lot of such small detectors, and each of the detectors must go around. So the convolution mask should go around all through the frame. So the mask should move from here to here to here to here to here to here. Means all throughout the frame the mask will move. Therefore, lot of features will be generated. See here. So the beak from different parts will be generated, and they will therefore contribute towards the richness of the content. So since the flow, or since the masking process is all throughout the frame, therefore the feature richness shall be here considerable, and that will be responsible for the reliability that the deep learning will generate. Now, how will the convolution layer work? Let's see that. So here is the input. So we will put here a filter. So the filter, we can call it with a big detector, but this particular filter will be a convolution mask that can be 3 by 3, that can be 2 by 2, that can be 4 by 4. So that will now, from this one, that will if it's 3 by 3, a 3 by 3 a group of values will be taken, and that will be now confined to one particular feature. Now this particular feature will be further more such dots will be generated, because this particular mask will move all throughout this frame. So many of such features, many of such dots will be generated. You see how that is done. So here is the 6 by 6 frame. So you have the filter mask. These are 3 by 3. So all these 3 by 3 filter masks shall be generating, or shall be detecting small patterns. These will be all tasks for such sort of a purpose. And you see how it is linked. Dot product. So now this one is called stride. Means when you move from this slot to this slot, if you go through by one small square, that is called a stride. Now you can have stride of 1. You can have stride of 2. Stride of 2 means you jump from this particular location to this particular location, and then do the dot product. So if stride 2, so you see the shift. So that way. So this way, you will find that the feature map is generated throughout the case. You will have a feature map generated through this filter. So repeat this for all the filters. A complex feature map is generated. Now this particular feature map. So two 4x4 two 4x4 images forming 2x4x4 matrix. So quite a complex mixture of features generated. And now if you have color content, so this will be done channel wise. That will be done channel wise. So filter 1, filter 2. So now once you are through with the convolution part, you will be now connecting these feature maps to a fully connected layer. So the fully connected layer will look something like this. All of the features now converted to a form suitable for feeding a classifier, a classical feed-forward classifier. So the last layer can be a multi-layer perceptron. Before that, there will be only feature learning taking place. Lastly, that will be a classification process. So how the feature map is converted to a fully connected layer, this slide shows. So you see shared weights. So now the same thing when you do it for a face recognition purpose, cat or dog. So you feed the frames, cat or dog frames, convolution max pooling, convolution max pooling. These can be repeated many times. So depending upon the complexity of the content, these can be repeated many times, and finally you will be flattening them and then feeding them to a fully connected feed forward network, just like the multi-layer perceptron, and that will get the classification result. Now let's talk about the max pooling. Max pooling is some sort of a rounding off process. So with different filter masks, you can do different types of rounding off. So you can find here a max pooling layer doing work. So the max pooling layer will finally see that with different filter masks, a few of the values will be staying back. So from four different quadrants, just four different values will be only staying back. But these four different values will be the most crucial values required for doing the feature mapping or doing the feature generation. Since we saw there shall be 2 × 4 × 4, a huge set of features will be generated. That shall be more complex with the color content. Therefore, we need the max pooling to somewhat do a round off of the data generated, and the most relevant part will be only retained. So subsampling, with the subsampling pixels, we'll see that there will be no change in the content, but the size will be reduced. So a bigger frame will be turning out to be smaller. And then subsampling is required, because with subsampling we can reduce the computational requirements, memory requirement, and the processing requirement, computational cycles. So how we can do the max pooling? There is one such depiction. You need the image frame. You pass it through a convolution layer. Do a max pooling. A much reduced feature map will be generated. So each filter is a channel. So with the color, that will be 3 times more further. So if you do it further, do a max pooling there, so you can have a new frame generated, but that shall be of reduced content, but with deeper content. So that way you can make the process fast, and you can lower the computational load. You can lower the computational demand. So then finally we should see how the flattening is done. Flattening shall be to do a conversion from a multi-dimensional format to a one-dimensional format. So if you have a 4 × 4 feature map, that will be converted to a 1 × 16 vector representation in the row or column format, depending upon the structure of the classifier. So a flattening means how you reconfigure the feature map to make it suitable for the subsequent stage of classification. So this will go to a fully connected feed-forward network. The fully connected feed-forward network will use a supervisory training, or may use a supervised training to generate the decision. So now CNN is very widely used for speech recognition purpose. So in case of speech, you will use a time spectrogram. So the time spectrogram will represent the content, who said what, and what part represents which phoneme. So the time spectrogram will look something like this. These are time variations. This is a time scale, so it will show us time variation, and this being the frequency will show the variation of the spectral content spectral content variation with time. So that particular variation will have a uniqueness through which we can recognize a speaker or a speech content. So segment by segment, these are taken and fed to the CNN. So the filters move in the frequency direction like this. So how the feature maps are generated. These are the basic ways. So this will next move to the next part. That will move to the next part. That will move to the next part, and that will move to the next part. So this way, who said what can be recognized. So so in the time scale, this particular network structure will move. Now since we have the CNN, or have the deep learning doing the most its most decisive part is the feature learning. Therefore, in case of the feature learning, there will be some very distinct parts. So one shall be done with a feature extractor or a feature generator, G of F, GF of a few parameters. Then you will have a label predictor. From this feature generator, you will have a label predictor. So the label predictor will be primarily generating the label class, or the class labels, or the class codes. Now, while the class codes are generated, these will be fed to a domain classifier. Now, why this slide is shown is for the fact that this particular slide is used for cases where there are no data labeling. So if there are no data labeling, yet you need to do work, because data labeling for most of the cases is a very tedious task. Therefore, we can have a feature learning stage that can be used first for generation of the class labels, and then we can use a domain classifier for doing the discrimination with the use of the domain class codes generated by the label predictor. Then we can have a generative model for that will work, or that will use primarily the regression technique for generate different prediction stages. So you can have here the probabilistic models of the data that will permit the uncertainty to be captured. You can have here data distribution generated, or its probability calculated, and you can have high dimensional outputs generated. So you can have further the conditional density prediction also. Therefore, you can use this particular model for doing a whole range of tasks where there are no level data, and you have no provision of supervised learning. You are facing a unsupervised learning situation. So here can be a generative structure, a generative model, which will have a lot of learned content, learned content from a feature space, say Y1. So this Y1 will be unobserved. Then since L1s, L1, L12, L13 are generated by this generative structure, these will be observed cases. So this can help in doing a supervised learning. Then that particular know-how now can be used for generating a discriminative structure where there can be weakly supervised and strictly supervised structure. So therefore, we will have these type of uh, generative and discriminative structures doing doing the training, doing the learning, and permitting us to deal with unlabeled situation, unsupervised learning situation. So how they work, the discriminative and the generative structures, we will find that the discriminative structures will be laying a discrimination boundary for separating out the content, and the generative structure will be generating the label representations or the class labels through which the classification can be done. So if we now have very small trace of a photograph, so these discriminative and the generative structures can be used to scale it up, and then finally find that this particular small stretch is representing a chair. So these discriminating and the discriminative and the generative structures can be used for doing scaling up or restoration work. So mostly in drone photography, where the drone is flying in very high heights or in flying in heights, in great heights, from that you are trying to figure out what a small trace of the drone, a small trace of in a photograph is somewhat different from the rest of the contents in the photograph. So if you want to find out the details of that particular content, what to do then? You can use these particular structures, models, to generate the proper representation of that particular dot. These are used for remote sensing and surveillance purposes. So now these were all used with feed-forward structures. Then you have the deep recurrent networks. These have bidirectional structures through which you can deal with the speech content, sequencing, speech translation. So these are some of the works that are very relevant nowadays. So these deep learning, deep recurrent structures are used for these particular purposes. Then there is one more variation called the long short-term memory, the LSTM, very famous nowadays. These are used for mostly for time dependent cases. So in most of the cases with the recurrent structure, since there is the back propagation, so the back propagation makes its convergence and therefore the stability to be a critical factor. But with the use of the long short-term memory, you can get rid of a lot of those stability and the convergence problems. Therefore, these have nowadays become very popular for doing time sequencing, for doing speech translation, and for doing time series prediction, for forecast of stock market prices, for the forecast of the weather, so on and so forth. So with all these things, when you summarize, you primarily you need the probability knowledge, models, linear algebra. Then those things will give you the way to learn the optimization theory and the statistical learning theory. Then from that, the machine learning will develop. Machine learning going to deep learning will constitute the bigger picture of AI, which can use all the contents of computer vision, game theory, and natural language processing. These can be used for our day-to-day life. Most recently, a huge shift towards the robotics and all that, and control. Then we find that the state of art is that the most of the deep learning networks are used for the image capture generation. So Facebook's tagging part is based on this. So when you put some figure there, you tag it one time, that particular tagging shall be remembered for the subsequent cases. Same is the case with Google Photos. So you name somebody with a folder, and then put one picture of that person in that particular folder. Then rest of the photographs will go and get stored there in that particular folder, and then rest of the caption generation can be also done by the use of the deep learning. So this particular technology was reported first in 2015, long time back. Deep learning has been in the forefront for the last 10 years. Recently, its prominence is more. Mostly in the vision domain, computer vision domain, man-machine communication vision. Then lately it is coming into the non-linear dynamics, non-linear uh, uh, model generation. So lots of scientific works are being done with the help of deep learning. So those who have a grip on the deep learning tools, deep learning know-how, the sky is the limit now, since these are the people who are in big demand worldwide. So many sectors, features you will find. The speech recognition, then the OCR technology, face recognition, facial recognition, then the gate recognition, you name it. So in all these fields, deep learning has proven to be very successful and reliable. Most of the social media, Skype and Twitter, Facebook, these all use lots of deep learning tools and for lots of background processing and tracking. So we can come to the conclusion that deep neural networks are a recent structures of the DNN that primarily tries to mimic the human decision-making capability with less hardware dependence, but with much high levels of representations without much dependence on the data, but needs lots of data for doing the training. So training is based on supervised and unsupervised and mixture of both. Mostly deep learning have found to be very successful in speech processing and computer vision domains, with the sky being the limit for all these tools. These are some of the beneficial links that you can go through. So I would now like to request you all to raise a few questions. So I don't know how you have taken these presentations, but these are somewhat conceptual things. You need to have some amount of patience to learn them. They're at the beginning. Once you start to learn them and practice them, maybe in the MATLAB to start with, and then shift to Python uh, or Google Colab or to even TensorFlow, things will be much simpler. But to begin with, these are highly conceptual based content. So you need to spend some time to learn. Once you learn them, the sky will be the limit, since the world nowadays goes on with these sort of techniques. Basic things are that I presented. More of those can be built up later on. The whole discourse of deep learning remains. I just started today the basics. Subsequent things are there. A lot of things are there. I think the course was, or these lectures were beneficial to you all. If you have some doubts, you can raise those doubts. I shall be pleased to clarify the doubts. You need help, further help. I shall be uh, keen to help. So, with these few words, and I come to the end of this presentation, and shall be in touch with Dr. Kaplan for subsequent things. And thank you to you all.
Thank you.